We live in an individualistic society where systematically people are expected to take care of themselves with limited accommodations for differently abled citizens. Specifically, deaf citizens are especially vulnerable to dangerous situations with limited awareness, especially in public. From situations ranging from someone calling from behind to a potential train crossing accident, the safety of deaf citizens is severely underrepresented. Through our project, our main goal was to give power and a new level of awareness to deaf individuals. As a result, we created an AI wearable that turns omnidirectional noise into silent haptics.
I think for most of us, hearing is something we take for granted. But the reality is, hundreds of millions of people around the world suffer from disabling hearing loss, which is a massive challenge for them, especially in a society built on verbal communication. This is why we created an AI-powered directional sound device that users can wear, which provides real-time information about what and where sounds are coming from. Our goal is to not only assist those with hearing difficulties, but to also reduce social silence, when people are left out or unheard by the systems around them.
So going into our actual hardware, you can see an ESP32 camera here, which essentially acts as our Bluetooth module and also sends the pictures from behind the user to our phone and our live server. You can see here that there are three motors that are powered by three H-bridge motor controllers. And essentially, this allows these motors to be controlled much like a speaker. So it would vibrate at specific frequencies as intensity increases. Here we have the Arduino module that controls the motor drivers.
Okay, so I'll explain our backend, which is our AI and machine learning models. So after capturing incoming audio, we send it to OpenAI's GPT-4 audio model through an API request, which returns a short word or phrase describing the sound it detects. Using that sound description as well as inputs from both cameras, we then run a YOLO V5 computer vision model to identify the most likely source of sound. For example, if the audio model detects a car horn, the vision model will analyze the images for vehicles and draw a bounding box around the most likely source. Finally, after the vision model draws a bounding box, we analyze the pixels in the images to calculate the relative angle of the given object. Using this angle, we distribute power across the three motors accordingly using inverse distance weighting. So motors closer to the sound are stronger, allowing the user to tell where the sound is coming from.
Hello and welcome to the official demo. So to start off, we have to connect to the Arduino, like so, and we have to connect to the device, which is our network, like so. Afterwards, everything should show to be connected, and connected. And this allows us to start the camera and start the audio detection. And so here is the camera, and after I start it, it should show the back camera. And here, I'll start the mic. And it should start picking up sounds. Hello, hello, hello. And now it has picked up the sound. And here, if you take a look, it is detecting that the sound is coming from 3. And that is because the camera has noticed that I am closer to where the position of motor 3 is. If I move over here, it'll now detect that I'm closer to motor 1, because the camera has noticed that I've moved. And you can see this reflect in the actual sensory part of the device. And this is the neckwear. Camera, and we can start the mic and auto detection. And so, it will now detect that there's a human located in the back camera, and it'll start vibrating motor number 2, which is located in the back. If we zoom back out, we can notice that motor number 2 has its frequency gone up because there's audio detected, and they are detected in the back camera.